In this lecture on the design process, we're going to look at what is design, what is a design process, some design process examples, and then the design process we are specifically going to use in IED in this class. What do we mean by design? The word design is often used as a generic term that refers to anything that was made by human consciousness. So you can say, do you like the design of the new iPhone? Or the civil engineer designed a new bridge to cross the Elkhorn. It's also, the word design also is a process that is used to systematically solve problems. You may have a design for getting to school every day. Do you do the same thing every day? And the end result is it gets you to school. The alarm clock goes off. I wake up and go to the restroom. I take a shower. I brush my teeth. I eat some breakfast. I catch the bus. I get to school. Right? So that's a design process that you have to get you here so you can learn. What is a design process? ITEA has created the standard for technological literacy. And they say a design process is a systematic problem-solving strategy with criteria and constraints used to develop many possible solutions to solve or satisfy human needs or wants, and to narrow down the possible solutions to one final choice. Whew. That is a whole lot of words. Let's break that down so it's not quite so scary, because it's kind of scary the way it is right now. So, design process is a systematic problem-solving strategy. All that means it's a system for solving problems. Period. It's a system for solving problems with criteria and constraints. Criteria are what it must do, and constraints are what it must not do. Used to develop many possible solutions and narrow down the possible solutions to one final choice. So the design process is a way to solve problems that takes many possible solutions and picks the best one. So if we look at our picture over here, we have a sketch by Dr. Werner von Braun, and it's the first sketch of a rocket. And using the design process and a little bit of time, we eventually get to the part where we have the Saturn V rocket that's launching men into space. So let's quickly go through some various design processes. There are many. It depends on the field that you're in. It depends on the company you work for. It depends on what you personally like. So there's many of them out there, but it's still a system to solve problems. So here's an example. It's from Design and Problem Thinking in Technology. You see it has 9 different items. Identify problems, do a design brief, make some research, generate some solutions, choose a solution, create something, test and evaluate it, and then redesign and improve it. Let's look at another one. Design process number 2. Engineering, Drawing, and Design, the 3rd edition. So we're identifying a need, we're making some criteria, we're researching, we are generating solutions, we're picking a solution, we're creating a model or a prototype, we're testing and evaluating, and we are redesigning or improving as needed. So that one has 9 items as well. Let's go to number 3. This one is back from our buddies, the ITEA Standards for Technological Literacy. They say, number 1, define the problem. Generate some ideas and do research. Identify criteria and constraints. Create a model or prototype. Test and evaluate, and then redefine. All right, but they have 12 steps in theirs. This is the process that's used in IED. All right, so this is the one we're going to use in our classroom. We picked the best one. It's a little bit simpler, but if you will notice, it has exactly the same steps that we mentioned in the other one. We're going to define the problem. We're going to generate some concepts. We're going to develop a solution. We're going to construct and test a prototype. We're going to evaluate the solution, and then we're going to present the solution. I said exactly those same things with those other example parts. There's always the same steps going on. They just may call it something a little bit differently. So the design process and IED is an example of one design process. I've said that. Many design processes exist, and they are equally as effective. As long as you consistently apply a single, clearly defined process, everybody's on the same page and everybody's getting the job done. So you don't have to use the IED one once you become an engineer and do it in industry. You can choose and tweak it to make it work for you. But for right now, we're all going to use the same IED design process. The first step is defining the problem. You have to pick, identify, choose a problem to solve. The next thing you have to do is validate the problem. Is it actually a problem? Who says it is a problem? It's not enough that you say it's a problem. There must be evidence. There must be facts to support your claim that it's a problem. It must be something that somebody needs and somebody wants. And you have better have searched and looked to see if anybody else has fixed the problem before, because it doesn't make any sense to spend time and money solving a problem that the solution already exists. Next, when you're defining the problem, you must justify the problem. It must be proven that the problem is worth solving. And it's not always worth solving a problem. If you're going to spend $200 million to get $2,000 of increased sales, you've just lost the company that you work for a lot of money. So why, if it's a minor problem, would you spend an incredible amount of money trying to solve it? So you have to justify it. Is the problem worth solving? Once you say, yes, we have a valid problem and it's worth solving, then you have to create the design requirements. They're also called specifications or specs. Do you have the requirements? What do I need to do to solve the problem? They need to be specific in what needs to happen to consider it solved. All right. When you create the design requirements, you'll generate criteria and constraints. Criteria are what it must do. Constraints are what it must not do. It must lift 100 pounds. It must not break when I use it over 1 year. So you generate criteria, what it must do, and constraints, what it must not do. This is all brought together into a design brief. It is a document, a technical document that lists everything that needs to happen for you to solve the problem. And when you have the design brief fully put together, you have fully defined the problem. Let's look at design brief one more time. Let's define it real quick. A design brief is a written plan that identifies a problem to be solved, its criteria, and its constraints. Or to put it another way, what are we fixing? What must we do? What must we not do? It's used to encourage thinking of all aspects of a problem before attempting the solution. It ensures, when done correctly, that you've thought about all the little wrinkles and all the little facets of the problem to make sure you're covering everything so you don't get to the end of all the process and realize, oh, I forgot something. And all your work's for nothing. Once you have your design brief all complete, before you move to the next step, you need to stop and again say, is it valid and is it justifiable? And if the answer is no, in some cases, you may have to loop back and redefine the problem. Or you need to change your design brief to make it to where the problem is valid and justifiable. Is it truly a problem? And does it make sense to spend money and time fixing the problem? If you can't say yes to both of those, then you're going to have to loop back and redefine the problem or abandon the idea, the project altogether. Step 2 is generate some concepts. Now, once you have a design brief and you're ready to move into generating concepts to the second stage, the very first thing you are going to do is research. You are going to find out, what have other people done before me? What can I learn from what other people have done? Because if somebody else has spent thousands and thousands of hours solving a problem and you can take all of that, then you just saved yourself thousands and thousands of hours. Learn from others and use what they've learned. After you complete your research, then you could move into the brainstorming process. There's an entire PowerPoint slide on different ways to brainstorm, but you're going to come up in some method with additional ideas, additional solutions to this problem. You're going to say, here are many, 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 many ideas, and the ideas have lots and lots of ideas. Here are many ideas to solve this problem. Or during the research and during the brainstorming, you may discover something you forgot, and it is perfectly fine to stop and redefine your design brief based upon those additional goals. Sometime during research, you may discover something that you've missed. Sometime during your brainstorming session, you may think of something that's spectacular and you want to incorporate it into your design. Something new and novel that's never seen before comes out of your brainstorming session. It is perfectly fine to change your design brief, to loop back and go forth. In all steps of the design process, you can apply STEM principles. You can look at science, technology, engineering, and math and see, is there anything from those disciplines that can help me? Then once you have generated many solutions, many being way more than one or two, you need to select an approach. You need to focus your area. So we have this giant bucket of ideas, and then we need to pour out all the other ideas that don't work and just narrow it down to one idea still left in the bucket. So you're going to go very, very wide into a narrow one idea. So the method of selecting an approach that I like the best is the decision matrix. This is one way, but it makes you're able to select the best idea using logic and reason and not your gut, and that's important. So a decision matrix is a tool used to compare design solutions against one another using specific criteria. So you're going to say, these are the things that are important to the design. Here are my solutions, and when I compare all my solutions against this criteria, this one's the best, this one's the worst. All right, so here's an example. Across the top, we have cost, complexity, development time, and then we have a total. And then we have 6 ideas over here. Those 6 ideas are being ranked against one another. We have said at the bottom that 4 is the best and 1 is the worst. So we look at cost. The easiest way to think of this is look at all 6 designs. Which one's going to cost the most to implement? In this case, it's going to be idea number 1 and is probably the worst. If we look at which one costs the least, it looks like idea number 3 and idea number 5 are costing the least because they're ranked higher. And you're comparing them against each other. Here's complexity, with 4 being the best, the most or the least complex, because least complex is better. The least complex is going to be idea number 6, and then you see the ranking. Development time, shorter development time is better, right? So the best is going to be idea number 6, and idea number 4, and idea number 3. Those are all relatively the same development time, and it's very, very quick. We add all those up, And the highest number, in this case, number 6, becomes the idea that we want to go with. If technology doesn't exist that would allow development of the solution, you select the idea and it turns out to be hoverboards. You have to then decide, does the technology exist? Do I need to go and develop that technology? All right. So if the technology necessary to develop the solution does not exist, you may have to go into research to pursue a solution. So you may need to go out, do scientific research, and then loop back, make sure your problem is good, maybe make sure that your concept still applicable once you have created your scientific research. So you have to determine, do I need to do that? Do hoverboards exist now? No. Then we're going to have to go back and do research. Or is my best solution hoverboards? And I've determined that the scientific research needed is probably more than this project can justify. And so then I may have to go back and go loop back from here and regenerate concepts, because the concept that made the most sense in light of not having enough technology doesn't make sense anymore. So you have to use your brain, you have to use your logic and your reason. The next step in the engineering design process is develop a solution. You're going to create detailed designs that complete your solution. They are going to justify the solution path. So they are going to explain everything that someone from the outside needs to know to understand your item. And then they're also going to justify the expense and the effort needed to solve the problem. Because if you've chosen here in step 2 a very, very expensive solution, then it may not make very much sense based upon how much sales you're going to have to continue on with the project. So you have to develop a solution. This ultimately all leads into technical drawings. So technical drawings provide technical information necessary to produce a product. Many times, or all the time, it has its material, its size, and its shape. Sometimes it can be multiple parts, and so you'll have an assembly. It's important to not only know what the parts are made of and how they are shaped and how big they are, but if they go together, it's also very important to know how they are put together, and that's what an assembly drawing does. Once you have a solution and you have technical drawings, it is time to stop and once again think, is my solution valid? If it's not valid, is it not solving my problem? Does it cost too much to solve the problem? Then you may have to go back and return to a previous step in the design process and try again. Step number 4 is construct and test a prototype. You need to plan some prototype testing. A lot of students have a problem with this. There's a lot of work getting to this section. We've been talking for a number of minutes now, and that's just talking about the process. That's not actually doing the process. But once you have a prototype, you have a model that you hold in your hand and can function the way it's intended, you need to test that. And that's doing the test more than once, because the more repeatable the test is, the more solid your design is going to be. So you can look at your testing from a performance point of view. Does it perform as expected? Or, for example, every time it gets hot, it stops working. All right. Usability. If I hand it to somebody who doesn't know anything about it, are they able to figure it out? Are they able to operate it? Or do I need to give them hours and hours of instruction? Is it also usable in different environments? If I have my new item and when my hands get sweaty and I use it outside, I can't hold it. I keep dropping it and it breaks. Is that a problem? Durability. When I drop it, does it break? Is that an expectation? So the expectation you have on durability for your soda can, all right? No one expects to be able to drop that numerous times and have it survive with the soda intact. But I do have the expectation as a store owner to ship it across the country and get it to my store and unpack it from the truck in a protective carton without it leaking and destroying product. So there is an expectation of durability that you need to test your prototype for. So when you're testing a prototype, you need to always collect the test data, make certain that it goes into your engineering notebook, make certain that you record that, make certain that you collect more than one test. You need to think about and analyze the test data. What does it mean? Is it valid? Did I construct the test properly? Is it testing for what I want to test? Because sometimes it gets very difficult to determine, is it a valid test? The last thing that what this all leads up to is a test report. So you have a test report that determines or shows, illustrates all the different tests you did to it, how it performed, and that is now acceptable or not acceptable to move forward. So you have your test report. You need to determine, is the prototype valid? You have your design brief. You can go back. Does it solve everything? Yes, 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 yes. Is it durable? Is the performance good? Is the usability good? If that's all yes, you're ready to go to the next step. If it's no, then maybe you need to jump back to a step or two. Maybe all the way back to the first and redefine your problem. Maybe generate some more concepts, but you're going to have to go back if the prototype isn't working right. If a testable prototype cannot be built or test data analysis indicates a flawed design, the designer must return to a previous step of the design process. So that's just what I just said. If it doesn't work the way you intended, you can't go forward. Step number 5 is evaluate the solution. You are going to look at how effective your design is. What you've come up with to solve the problem. How well does it work? You're going to reflect on the design. You're going to think about how well does it work? Are you happy with it? Or can you recommend some improvements? You may optimize or redesign the solution, returning to prior design steps if you need to. You may need to revise design documents. You may change your design brief. You may change your technical specs. You may change your technical drawings. You may go back and retest because you're not comfortable with the amount or type of testing that you did. So you're evaluating the solution. Does it solve the problem? And will it be durable, usable, and perform well once you release it into the wider world? At the end of this, you create a document that's your project recommendations. I recommend that we add an additional layer of paint because we're getting scratches, and maybe a clear coat to prevent scratching. You may say, I recommend that there's no changes and we go immediately into production, but you're going to make recommendations and justify those recommendations to the people that are funding your project. Every time you complete a stage or a gate or a step in the design process, you always have to take a moment and say, is it solving the problem or not? So here we have finished the evaluation. We have looked at our design brief. Does it meet the design brief? We've looked at our technical drawings. Are the technical drawings up to date, current? Do they say everything they need to say? Does our prototype work? Is it usable? Is it durable? Does it perform as we expect? We look at the test data. Does the test data, did we test it enough? Did we test it in the right way? Putting all that together, are we comfortable releasing this into the wider world? Do we ship it to the customers? Or do we go back and fix it? Does it solve the problem? If it doesn't, the designer must return to a previous step in the design process. You have to loop back and fix it and solve the problem. The last step is present the solution. This is where you finish the documentation of the project. You may have a project portfolio. These are very, very important because you may move to another company. The other people on the team may move somewhere. They may take another job, and that knowledge that you have on that project is lost. So your project portfolio allows somebody to come in and make changes and iterate the project and make an innovation to the project without knowing everything or having you in front of you, because they have everything that you knew inside the project portfolio. You're going to communicate the project to the wider world. You may release it in the form of a formal presentation. Here is the conclusion to our steps. A lot of times, this is a final presentation to your boss's boss. And this is the point where you are asking for money. We have solved this problem. Here's the problem. Here's how we solved it. We now need $2 million to implement it. Can I have $2 million? And let me tell you, how comfortable are you giving somebody $2 million? So you need to be able to justify how you're solving the problem, why you're solving the problem, and why your solution is the best way to go forward. That's the end of the design process. That's all 6 steps that we're using in IED. Now, I may have presented this in somewhat linear fashion. I started with step number 1. I went through step number 6. The problem with that is, well, I did it because it's the easiest way to do it. The problem is, it's rarely the way the design process works. It's rarely straightforward. Designers must evaluate, reflect, redefine, and redesign throughout the process. It is very common to repeat steps of the design process several times before you get a solution. And so you're going to step back. And that's called iterative. It's an iterative process. You're going to step back. It repeats itself over and over until you get the desired outcome. Once your solution is out there released to the world, there may come a time where you need to improve that solution. So if you go back and improve it or redesign it, it will require you to repeat this whole design process. Going back and improving a product starts this product innovation cycle. And you can see it all throughout history how it occurs. We have the phonograph by Thomas Alva Edison. He patented it, and for 20 years no one else could make a similar device that met his patent because he had a monopoly on that. But at the end of the 20 years, anybody could, and you could also make improvements to that. So we had in the 70s, we had the creation of the cassette tape, the audio cassette tape, which is an improvement on the photograph. And then in the 2000s, the product life cycle continues because now we have the first iPod, also an instrument for listening to music, and that cycle just goes on and on and on and on.